In the YouTube video titled Lecture 5, Data Encryption Standard, DES Encryption by Christof Paar, Professor Christof Paar commences by situating the current lecture within the broader context of the course, emphasizing a shift from the previous 2 weeks' focus on stream ciphers to the discussion of block ciphers. The Data Encryption Standard, DES block cipher, specifically, will be the subject of the lecture. Professor Paar delves into the historical genesis of DES, highlighting its conception by IBM in 1974 with input from the National Security Agency, NSA. He underscores that the standard was initially kept confidential, with the public release limited to the cipher itself. This deliberate obfuscation, Professor Paar argues, was driven by the U.S. government's intention to create a broadly adopted commercial standard while maintaining the cipher's efficacy for governmental purposes. DES's consequent prominence within the field has made it the subject of extensive academic scrutiny, and for a substantial period, it was the dominant cryptographic tool in practical applications. Professor Paar then embarks on a thorough exposition of block ciphers, delineating their fundamental differences from stream ciphers. While stream ciphers operate on individual bits, block ciphers encrypt data in discrete blocks, with DES employing 64-bit, 8-byte blocks. The significance of key size within block ciphers is then accentuated, with DES utilizing a 56-bit key. He subsequently introduces the cornerstone concepts of confusion and diffusion in block cipher design. Confusion, Professor Paar explains, aims to obscure the plaintext-ciphertext relationship, often achieved through substitution tables. Diffusion, on the other hand, involves dispersing the influence of each plaintext bit across multiple ciphertext bits, commonly accomplished using permutations. He underscores that the optimal block cipher incorporates both confusion and diffusion, a principle that underpins the design of numerous modern block ciphers. The lecture then proceeds to dissect the internal workings of DES, commencing with a high-level overview of its structure. DES comprises 16 rounds, each round processing a 64-bit data block and generating a corresponding 64-bit output. Professor Paar emphasizes that the initial permutation, IP, and final permutation, IP superscript 1, are comparatively inconsequential operations. The core of each round is the intricate F function, which is deemed super important by Professor Paar. This F function takes a 32-bit data input and a 48-bit subkey to produce a 32-bit output. This output is then XOR'd with the left-hand half of the data block, followed by a swap of the two halves. Notably, the subkey derived from the 56-bit key is round-dependent. The F function is further decomposed into its constituent components: expansion, XOR, S-boxes, and permutation. The expansion box takes a 32-bit input and expands it to 48 bits, thus introducing diffusion by replicating each input bit across multiple output bits. The 48-bit output of the expansion box is then XOR'd with the 48-bit subkey, and the resultant 48 bits are fed into the S-boxes. The S-boxes, which are characterized as the heart of DES, are responsible for confusion. They accept a 6-bit input and produce a 4-bit output with 8 S-boxes in total. Finally, the permutation box acts on the 32-bit output of the S-boxes, rearranging the bits to enhance diffusion. The details of the S-boxes are then explicated, focusing on the tables that define their operations. Professor Paar highlights several noteworthy S-box properties. They are resilient against differential cryptanalysis, characterized by a robust nonlinearity property whereby a single-bit input change causes at least 2-bit output changes. These attributes contribute to DES's robustness against known attacks. The lecture continues by exploring the rationale behind the 64-bit block length and 56-bit key length employed by DES. Professor Paar contends that these design choices, motivated by the Cold War, aimed to achieve a cipher impervious to external adversaries. This led to a larger key size and a more intricate cipher structure. He then addresses the pervasive suspicions surrounding the NSA's influence on DES, particularly due to the existence of a backdoor, a mathematical means of compromising the cipher known only to the NSA. However, Professor Paar posits that the NSA likely did not include intentional backdoors, attributing the perception to the designer's dedication to a robust cipher and their strategic withholding of specific details. The initial permutation, Professor Paar clarifies, was solely a technical engineering decision. Professor Paar then vividly demonstrates the avalanche effect in DES. He does this by showing that a single bit change in the F-function input can lead to substantial output alterations. This avalanche effect is a crucial indicator of a strong block cipher, as it demonstrates that a minute alteration in the plaintext can significantly impact the ciphertext. The lecture concludes with a succinct summarization of the pivotal points discussed. Professor Paar emphasizes the significance of the S-boxes, which contribute to both confusion and DES's resilience to known attacks. He reiterates the complexity of DES design, stressing the importance of thorough comprehension for those involved in implementing or analyzing its security. From 0 minutes to 5 minutes of the video, Professor Paar welcomes the audience to Lecture 5, a continuation of the previous 2 lectures on stream ciphers. He reminds the audience that they have explored stream ciphers in depth, and today's focus will shift to block ciphers. He emphasizes the practical significance of block ciphers, noting they are likely utilized in 95% of real-world applications, including crucial areas like internet browsing and online banking. He then provides a roadmap for the upcoming lectures, highlighting that the Data Encryption Standard, DES, will be the subject of the next 2 weeks, while the Advanced Encryption Standard, AES, will be covered in weeks 3 and 4. From 5 minutes to 10 minutes of the video, Professor Paar embarks on a detailed examination of the construction of a block cipher, utilizing the Data Encryption Standard, DES, as a paradigmatic example. He underscores the critical significance of 2 fundamental principles: confusion and diffusion. Confusion, often implemented through substitution tables, obfuscates the relationship between plaintext and ciphertext, making it difficult for an adversary to decipher the encryption process. Diffusion, on the other hand, aims to dissipate the influence of individual plaintext bits across multiple ciphertext bits, typically achieved through permutation operations. Paar proceeds to characterize DES as a product cipher, emphasizing that it iteratively combines confusion and diffusion operations. To elucidate this concept, he dissects a single round of DES, which entails partitioning the 64-bit input into 232-bit halves. The right half is then subjected to the F function, often referred to as the heart of the cipher, followed by a swapping of the 2 halves. The F function, in turn, incorporates an expansion operation, augmenting the 32-bit input to 48 bits. This expansion is accomplished by connecting certain input bits to 2 output positions, thereby ensuring that a modification to a single input bit propagates to multiple output bits. The speaker then delves into the key XOR operation, wherein the expanded 48-bit data is XOR'd with the 48-bit subkey. He highlights the indispensable role of S-boxes within the F function. These S-boxes execute a substitution operation, transforming 6 input bits into 4 output bits. Paar elaborates on the intricate design of S-boxes, which are meticulously crafted to thwart differential cryptanalysis, a powerful attack that exploits the correlation between plaintext modifications and resulting ciphertext alterations. He elucidates the construction of S-boxes using a table comprised of 64 entries that are accessed based on 6 input bits. The middle 4 bits dictate the column selection, while the outer 2 bits determine the row selection. Paar then transitions to the permutation P-box, demonstrating its pivotal role in DES. The P-box meticulously rearranges the 32-bit output from the S-boxes, maximizing the avalanche effect. This effect, a key indicator of cryptographic strength, measures how rapidly a change in plaintext propagates throughout the entire ciphertext. In DES, a single bit flip in the plaintext typically propagates across the entire ciphertext within 6 to 8 rounds, underscoring the algorithm's robust security properties. From 10 minutes to 15 minutes of the video, Professor Paar delves into the fundamental principles of block cipher construction, emphasizing the concepts of confusion and diffusion as articulated by Claude Shannon, the seminal figure in information theory. Confusion, in this context, aims to obfuscate the direct relationship between plaintext and ciphertext, often achieved through substitution techniques. The speaker cites the Caesar cipher as an example of a cipher relying primarily on confusion. However, Shannon emphasized that confusion alone is inadequate. He introduced the principle of diffusion, which seeks to disperse the influence of each plaintext bit across multiple ciphertext bits. Professor Paar clarifies that permutation, the process of reordering bits, is a common method to achieve diffusion. He illustrates this with a scenario. If a single plaintext bit is flipped, the resulting ciphertext should display alterations in multiple bits. This avalanche effect is an essential characteristic of robust block ciphers. Particularly salient is Professor Paar's explanation of how combining confusion and diffusion in a layered manner, resulting in a product cipher, forms the core of many secure block cipher designs. This process entails alternating confusion operations, like substitution, with diffusion operations, such as permutation, effectively intertwining the two for enhanced security. From 15 minutes to 20 minutes of the video, Professor Paar delves into the fundamental principles elucidated by Claude Shannon for constructing robust block ciphers. These principles, known as confusion and diffusion, form the cornerstone of modern cryptographic design. Confusion, he explains, entails obfuscating the relationship between plaintext and ciphertext, thereby rendering it challenging for an attacker to discern the underlying plaintext from its encrypted form. Paar illustrates this concept with the example of a substitution table, where each input value is mapped to a unique output value based on a predetermined mapping, effectively concealing the plaintext structure. Diffusion, on the other hand, emphasizes the dispersion of the influence of individual plaintext bits across numerous ciphertext bits. This ensures that modifications to a single plaintext bit result in widespread changes within the ciphertext, making it difficult for attackers to exploit localized patterns. Paar exemplifies this through the use of permutations, where bits are systematically rearranged, effectively obscuring the correlation between plaintext and ciphertext. To achieve a high level of cryptographic strength, Professor Paar highlights the necessity of iteratively applying both confusion and diffusion in a process known as a product cipher. This iterative process, he explains, involves repeatedly applying confusion and diffusion operations, each layer contributing to the overall security of the cipher. From 20 minutes to 25 minutes of the video, Professor Paar delves into the concept of diffusion, a fundamental principle in the construction of robust block ciphers. He elucidates that diffusion entails the dispersion of the influence of each plaintext bit across numerous ciphertext bits, thus obscuring the relationship between the plaintext and ciphertext. A salient example of this principle is a permutation, which involves the systematic rearrangement of the bit ordering. He underscores that a robust block cipher does not merely implement confusion and diffusion once, but rather iterates these operations numerous times consecutively, thereby creating a product cipher. This concept is graphically illustrated using a diagram that depicts a plain text X undergoing multiple rounds of confusion and diffusion, culminating in the ciphertext Y. Professor Paar then provides a detailed exposition of the DES algorithm, which comprises 16 rounds, each characterized by a specific sequence of operations. He meticulously dissects the steps involved in a solitary round. Initially, the 64-bit input is partitioned into two 32-bit halves. The right half is subsequently fed into the F function, a critical component of the DES algorithm, which generates an output based on the input and a round-specific subkey. The output of the F function is then XOR'd with the left half, yielding a new left half, L1. Finally, the left and right halves are interchanged, resulting in the output of the round. From 25 minutes to 30 minutes of the video, Professor Paar delves into the architectural underpinnings of modern ciphers, particularly those employed in the German e-passport. He underscores that a significant portion of these ciphers are constructed upon a Feistel network framework. This framework comprises 16 iterative rounds of encryption, each involving a sequence of defined operations. A salient feature of the Feistel network is the incorporation of S-boxes, which are essentially lookup tables that accept 6 input bits and generate a corresponding 4-bit output. These S-boxes perform a substitution operation, constituting a core component of the cipher's confusion aspect. Professor Paar emphasizes the meticulous design of these S-boxes to resist differential cryptanalysis, a potent attack technique discovered in 1990 by Adi Shamir and Eli Byam. From 30 minutes to 35 minutes of the video, Professor Paar delves into the intricate workings of the Data Encryption Standard, DES, a foundational symmetric block cipher. He emphasizes that DES, despite its age, remains a prominent cipher and a subject of extensive analysis. Paar explains that DES is a round-based cipher, employing 16 rounds of encryption to achieve its security. Each round involves a series of transformations applied to a 64-bit plaintext block. Professor Paar outlines the fundamental stages of a round, beginning with the division of the plaintext block into two halves, each containing 32 bits. The right half undergoes a critical transformation within the F function, the heart of DES, which receives both the right half and a round-specific subkey as input. The output of the F function is then XOR'd with the left half, resulting in an intermediate ciphertext. Professor Paar elaborates on the crucial F function and its internal operations. He highlights that the expansion box, responsible for increasing the size of the right half from 32 to 48 bits, serves as a critical diffusion element. This expanded right half undergoes a key-dependent XOR operation with the subkey, followed by a series of substitution operations performed by the S-boxes. Finally, the output of the S-boxes undergoes a permutation operation before being XOR'd with the left half, thus completing the round transformation. The process is repeated for a total of 16 rounds, culminating in the final ciphertext output. From 35 minutes to 40 minutes of the video, Professor Paar delves into the fundamental principle of diffusion in block cipher construction, underscoring its crucial role alongside confusion. He emphasizes that merely employing substitution techniques, confusion, is insufficient to create a robust block cipher. A strong block cipher, he explains, necessitates the iterative application of both confusion and diffusion operations. This involves a cyclical process of applying a substitution operation, followed by a diffusion operation, and repeating these steps to achieve a high level of security. He illustrates this principle by examining a rudimentary block cipher where the plaintext, X, undergoes a series of confusion and diffusion operations, culminating in the ciphertext, Y. This process, known as a product cipher, forms the bedrock of block cipher construction. He further clarifies that this construction approach, involving the repeated alternation of confusion and diffusion operations, is a key principle in the design of secure block ciphers. From 40 minutes to 45 minutes of the video, Christof Paar elucidates the construction of block ciphers, introducing two foundational principles: confusion and diffusion. Confusion mandates that the correlation between plaintext and ciphertext be obscured, effectively concealing the underlying relationship. Diffusion, on the other hand, dictates that the influence of individual plaintext bits should be disseminated across a multitude of ciphertext bits, thereby obscuring the direct link between input and output. Paar demonstrates that a rudimentary substitution table, exemplified by the Caesar cipher, solely provides confusion, while a permutation can be employed to introduce diffusion. The core tenet of block cipher construction lies in the iterative application of both confusion and diffusion elements to enhance cryptographic strength. Paar then employs a simple diagram featuring an 8-bit cipher to illustrate these principles in action, demonstrating that a single bit flip in the plaintext can result in multiple bit flips in the ciphertext, showcasing the diffusion effect. This visual representation provides a concrete example of how the principles translate to a practical block cipher scenario. Next, Paar delves into the intricacies of the initial permutation, IP, in the Data Encryption Standard, DES. He explains that the IP is essentially a bit permutation and provides a straightforward example to highlight its functionality. He clarifies that the IP functions by relocating bits. For instance, bit number 1 is copied to bit position 40, while bit number 48 is moved to bit position 1. Importantly, Paar emphasizes the reciprocal nature of the IP and its inverse, stating that if 64 bits are input into the IP followed by the inverse IP, the original data is restored. Paar further elaborates on the IP's mechanics using specific numerical examples, demonstrating the simple nature of the process and its ease of implementation. He underscores the complementary relationship between the IP and its inverse, illustrating that feeding 64 bits through the IP and subsequently through its inverse results in the recovery of the initial data. Paar concludes this segment by emphasizing the paramount importance of the IP in DES's security. He explains that if the IP were merely a simple permutation, it would be readily accessible to attackers, enabling them to reverse the process. This necessitates a more intricate IP design to thwart such attempts. Paar points out that while the permutation itself is not confidential, the IP's implementation is kept under wraps. This section of the video underscores the criticality of meticulous design in cryptography, highlighting that even seemingly straightforward elements can significantly impact the overall security of a cryptographic system. From 45 minutes to 50 minutes of the video, the speaker delves into the intricacies of the initial permutation IP function employed in the DES algorithm. This function serves to rearrange the order of input bits, effectively shuffling their positions. To illustrate this concept, the speaker presents a specific example. Input bit number 1 is reassigned to position 40, while bit number 48 assumes position 1. This transposition, however, is merely a straightforward bit permutation that has been publicly accessible since 1974. The speaker then examines the rationale behind the inclusion of IP in the DES structure. He posits that this function does not contribute meaningfully to the overall security of the algorithm, as a potential attacker could easily reverse the permutation. The primary purpose of the IP function, as elucidated by the speaker, lies in practical engineering considerations, specifically related to the physical movement of data within a chip. This emphasis underscores the historical development of DES as a solution to real-world engineering constraints. The speaker also addresses a pervasive misconception surrounding the IP function. He debunks the notion that the NSA intentionally designed DES to be less efficient in software implementations, thus incentivizing the purchase of hardware versions. This claim is refuted by the speaker's explanation that the two permutations within DES introduce minimal performance overhead in software environments, making their impact negligible. From 50 minutes to 55 minutes of the video, Professor Paar delves into the intricate workings of the S-box, a crucial component of the Data Encryption Standard, DES algorithm. He aptly refers to the S-box as the heart of DES, highlighting its pivotal role in the encryption process. He emphasizes that the S-box is responsible for the confusion operation within DES, a core principle of cryptographic design that aims to obscure the relationship between plaintext and ciphertext. He elaborates on the S-box's operation as a lookup table, where a specific set of input bits is mapped to a unique set of output bits. He explains that the S-box, in its essence, performs a nonlinear substitution, taking 6 input bits and generating 4 output bits. There are 8 distinct S-boxes within DES, each denoted as S1 through S8. Each S-box comprises a table containing 64 unique numerical entries. To illustrate the S-box's functionality, the speaker presents an example. He demonstrates how to identify the corresponding output bits for an input of 37. First, he converts 37 to its binary representation, yielding 00100101. Next, he extracts the middle 4 bits, 0010, which correspond to a column number of 2 in binary representation. Finally, the remaining 2 bits, 01, representing 1 in decimal, determine the row. Professor Paar underscores the significance of committing this table to memory for aspiring cryptographers, emphasizing its value as a practical tool in the field. From 55 minutes to 60 minutes of the video, Professor Paar delves into the intricacies of the S-boxes, a pivotal component of the Data Encryption Standard, DES algorithm. He elucidates that each S-box functions as a nonlinear substitution table, accepting a 6-bit input and producing a 4-bit output. The speaker emphasizes the non-trivial mapping process within each S-box. A 6-bit input word uniquely determines an output, and this selection is achieved by partitioning the 6 bits. The middle 4 bits act as a column selector, with columns ranging from 0 to 15, while the outer 2 bits function as row selectors, with rows also numbered from 0 to 3. To exemplify the S-box's operation, Professor Paar examines the decimal input 37. This input is initially converted to its binary representation, yielding 00100101. The middle 4 bits 0100 specify column 4, and the outer bits 01 indicate row 1. Consulting the S-box table, the intersection of column 4 and row 1 reveals the number 12. However, Professor Paar acknowledges a discrepancy in his table and rectifies it to 14, leading to an output of 1110, equivalent to 14 in decimal. Professor Paar underscores the S-box's crucial contribution to the principle of diffusion within secure block ciphers. Diffusion aims to disperse the influence of a solitary input bit alteration across numerous output bits. He illustrates this by demonstrating how a solitary bit flip within the input might cascade into multiple output bit flips after traversing the S-boxes. This cascading effect amplifies the impact of the initial change as it propagates through subsequent permutation and XOR operations within the DES algorithm. This intricate mechanism ensures that a minute input alteration can substantially affect the output, thereby enhancing the cipher's overall robustness against cryptanalytic attacks. Professor Paar concludes this segment by highlighting the deliberate design of the S-boxes to thwart differential cryptanalysis, a formidable attack strategy that exploits the relationship between input and output bit flips. The deliberate arrangement of values within the S-box tables renders it challenging to predict the propagation of a bit flip through the cipher, effectively undermining the efficacy of differential cryptanalysis. He concludes this section by noting that the S-boxes are fundamental to DES, a cipher once widely considered unbreakable until researchers discovered vulnerabilities, emphasizing the relentless pursuit of cryptographic security. From 60 minutes to 65 minutes of the video, the speaker delves into the intricate workings of the F function, a pivotal component of the Data Encryption Standard, DES algorithm. This function operates on a 32-bit block of data, transforming it through a series of nonlinear operations to generate a 32-bit output. The F function functions effectively as a pseudorandom keystream generator, adding complexity to the encryption process. Within the F function, the speaker highlights the significance of the expansion box E, which expands the 32-bit input into a 48-bit block, and the XOR gate, which combines the expanded data with a 48-bit subkey. However, the core of the F function's intricate behavior lies within the S-boxes, 8 unique lookup tables that employ nonlinear substitution. Each S-box maps 6 bits of input to 4 bits of output, creating a complex non-one-to-one relationship between input and output. The speaker illustrates this nonlinearity by demonstrating that an input of 000000 results in an output of 1100 in the S1 box, while an input of 111,111 yields an output of 1101. These S-boxes are paramount to understanding the security of DES, as they introduce a crucial element of confusion to the encryption process. Finally, the speaker concludes his explanation of the F function by outlining the role of the permutation box, P, which reorders the output bits, further enhancing the obfuscation of the original data. From 65 minutes to 70 minutes of the video, Professor Paar delves deeper into the Data Encryption Standard, DES, algorithm, concentrating on the pivotal role of the S-boxes. He elaborates that each S-box functions as a lookup table, receiving 6 bits as input and generating 4 bits as output. He underscores the critical importance of memorizing these tables, which will serve students well in future cryptographic endeavors. Professor Paar illustrates the functioning of these tables by meticulously demonstrating the conversion of a decimal input, 37, into its binary equivalent, 001000101. He then guides the audience through the process of determining the output bits for this input. The middle 4 bits of the input, 0100, are utilized to select the column, while the first and 6th bits, 01, are employed to select the row. This row and column selection ultimately yields the output bits 1101. Professor Paar emphasizes that the S-boxes are meticulously crafted to withstand differential cryptanalysis, a potent attack methodology. He concludes by stressing that the S-boxes are indispensable to the robustness of the DES algorithm, posing significant challenges to potential attackers aiming to compromise the encryption. From 70 minutes to 75 minutes of the video, the speaker delves into the intricate workings of the F function within the Data Encryption Standard DES algorithm. He emphasizes the paramount importance of comprehending this function, as it constitutes the core of DES's operational mechanism. The F function, acting as a pseudorandom keystream generator, accepts a 32-bit input and produces a 48-bit output through a carefully orchestrated sequence of transformations. The speaker elucidates that the F function comprises 4 fundamental elements: expansion, XOR, S-boxes, and permutation. He commences by expounding on expansion, where the input bits undergo a process of expansion from 32 to 48. This expansion, a form of bit permutation, involves connecting certain bits to 2 distinct output positions. For illustrative purposes, the speaker demonstrates that bit 1 is linked to both bit positions 2 and 18, introducing a degree of diffusion into the process. From 75 minutes to 80 minutes of the video, the speaker delves into the intricacies of the S-boxes, a pivotal component of the Data Encryption Standard, DES algorithm. He elucidates that each S-box functions as a lookup table, ingesting 6 bits of input and generating 4 bits of output. The speaker then embarks on a pedagogical exploration of the mapping of input bits to output bits within these S-boxes. He asserts that, for example, input bit number 58 is mapped to output position number 1. The speaker highlights the unconventional methodology employed by the S-boxes in selecting columns and rows, emphasizing that the middle 4 bits guide column selection, while the outer 2 bits determine row selection. To further clarify this principle, the speaker undertakes a systematic demonstration of the S-box's operation, using an illustrative input value of 37. He meticulously shows the conversion of 37 into its binary equivalent, 00100101, and subsequently demonstrates how the middle 4 bits, 0100, select column number 4, while the outer 2 bits, 01, select row number 1 within the S-box. The speaker concludes this segment by underscoring the paramount role of the S-boxes in engendering confusion, an indispensable element in the construction of a robust cipher. From 80 minutes to 85 minutes of the video, Professor Paar delves into the intricate workings of the S-boxes, the core components of the Data Encryption Standard DES algorithm. Each S-box functions as a substitution table, processing 6 input bits and generating a 4-bit output. The DES cipher incorporates 8 distinct S-boxes, designated S1 through S8. To illustrate the S-box mechanism, Professor Paar elucidates the selection process of output bits based on input values. The middle 4 bits of the 6 input bits serve as an index to select a specific column from a set of 16 columns. Concurrently, the outermost 2 input bits determine a row out of 4 potential rows. As an example, if the input is 37, which translates to 100,101 in binary representation, the middle 4 bits, 0010, designate column 2, while the outer 2 bits, 11, correspond to row 3. The output value is obtained by identifying the intersection of column 2 and row 3 within the S-box table. Professor Paar underscores the meticulous design of the S-boxes to withstand differential cryptanalysis, a potent attack strategy predicated on the correlation between input and output difference patterns. The S-box architecture is meticulously crafted to ensure that a single bit alteration in the input inevitably triggers a minimum of 2-bit changes in the output, effectively hindering the efficacy of the differential cryptanalysis attack. From 85 minutes to 90 minutes of the video, Professor Paar delves into the intricate workings of the S-boxes, which he asserts constitute the core of the DES algorithm. He underscores that each S-box is, in essence, a lookup table that maps 6 input bits to 4 output bits, thereby embodying a non-injective substitution process. These S-boxes are instrumental in achieving the crucial cryptographic principle of confusion, obfuscating the relationship between the plaintext and ciphertext. He elucidates how the input bits are employed to pinpoint a specific column and row within the S-box. The central 4 input bits determine one of the 16 columns, denoted in binary, while the remaining 2 bits identify one of the 4 rows, also represented in binary. He then exemplifies this process using the decimal value 37 as input. The initial step involves converting this value to its binary representation, 100101. Next, he isolates the middle 4 bits, 0010, which correspond to column number 2, and the outer 2 bits, 10, signifying row number 2. The output is then retrieved from the S-box table at the intersection of column 2 and row 2. Professor Paar clarifies that these S-boxes are not governed by a deterministic rule, but rather generate outputs in a seemingly random and confounding manner, contributing significantly to the algorithm's resilience against cryptanalytic attacks. He further explains that DES comprises 8 distinct S-boxes, each with its unique lookup table. These tables are meticulously crafted to effectively resist a formidable attack known as differential cryptanalysis. In summary, the S-boxes form a critical component of the DES algorithm, serving as the foundation for achieving confusion and bolstering the algorithm's resistance against cryptanalytic assaults. Despite their inherently complex and counterintuitive nature, They play a paramount role in the robustness of DES, ensuring its security against potential attacks. From 90 minutes to 93 minutes of the video, the speaker delves deeper into the internal workings of the Data Encryption Standard, DES, specifically the F function and its components, with particular emphasis on the S boxes. He emphasizes that the S boxes are crucial for DES's security, acting as substitution tables where a 6-bit input word maps to a 4-bit output. The speaker highlights the non-one-to-one nature of these substitutions, arising from the disparity in input and output bit lengths. He then details the S-box's organization. It comprises 16 columns and 4 rows, with the middle 4 input bits determining the column selection and the remaining 2 bits choosing the row. Illustrating the S-box application with the input value 37, binary, 00100101. The speaker demonstrates how the central 4 bits, 0-100, identify column 4, and the outer bits, 01 and 01, indicate row 3. The speaker emphasizes that the S-box table lacks any inherent pattern or rule, presenting a seemingly random configuration meticulously chosen for its cryptographic strength.